Okay, let's see today's topic. So this far what we have had, just a moment, I turn off my mobile phone. We have had the signals, and then we basically started looking at the system. So signals generation means that we actually generate, for example, a test vector, the delta function or step function or some sinusoidal function or whatever. We can generate this one plus some noise. Okay, good. And then we can actually also generate a system which is defined by its transfer function or difference equation. Basically, it has the system coefficient AK and BK, which in MATLAB are vectors. B0, B1, and so on, A0, A1, and so on. Okay, by the way, you also played a bit with the linearity and time shift invariance and such kind of things. Actually, if you find systems so that you can show it with these two parameters, then we know this linear and time shift invariance. Easy. On the system analysis side, you already know that, okay, if you calculate the zeros and poles from here, so if you calculate the zeros and poles, and if all the poles are inside of the unit circle, something like that, for example, from the second exercise, then you know that the system is stable. So we know also the stability. Linear time shift invariant. The causality, well, causality is more or less like, okay, this is also causal if we have both A and B start with non-zero value on the beginning. Okay. Today what we are going to do is we will take a look at what kind of responses these systems actually do have. There we go. So responses. So for example, what happens if we feed in impulse function? What comes out is actually the impulse response. Okay? Or how about if we feed a sinusoid function? What comes out actually is the magnitude response times the sine with some phase shift. Same way as in analog systems. Okay, but let's go and take a quick look at this theory part. So system responses. And yes, impulse response is nothing more than having the input, the impulse function as an input, and what comes out is the impulse response. Okay, nothing more than that. So for example, for the 4-point running average filter, the impulse response is quite straightforward. It's just this, you replace the x with the delta function. That's it. And it looks like kind of what you have already generated on the second exercise. Oh, was it on the first one? First exercise? Yep. Um, Based on the impulse response, we can actually divide these systems into two categories. One is the finite impulse response systems, meaning simply that, okay, our output has an ending. If you feed in a impulse function, does the impulse response actually go to zero at some point and stay zero? So that means that our impulse response is finite. Infinity means that it never ends. It's like any analog filter, RC filter. It decays but never goes exactly to zero. So it goes very close but never exactly zero. Okay. So, for example, that 4-point running average filter is FIR because, well, after the 4th time delay, the signal is zero on the output. Okay, impulse response. Same way, actually, these sampled analog systems, they are infinite impulse response systems. If you take a sample of the start sampling the response of, well, step response of a RC filter, then it's never ending decaying signal. On the system, basically, on the second exercise, there was this feedback element. The feedback itself, it's required to have an IIR system, but it still can be FIR if you find one feedback. I think I have the explanation part. No, it's not here. It was basically on the last time this slides somewhere. So we have 4-point running average filter block diagram looks like this. Okay, not like that. It's N, and then we have that 1/4 delay. Not those. Sorry. This is one way of showing the 4-point running average filter, but on the other hand, we also had this other way of showing it. It was the 4 times delay, and then let's see, -1 here. That's 1/4. And then we had this previous value of output. And here we have the sum, okay, something like this. So it has a feedback element right here. That's the feedback when we take part of the output and put it back to the input, same way as you would do on the feedback on the analog system. Same thing. Okay, yeah, but we have a feedback, but it is FIR system since it's defined by what this impulse response actually looks like when it comes out. Okay. Couple of words about the transfer function and impulse response. So actually, if you have linear time invariant system, then the transfer function is actually the same as Z transform of the impulse response. So if we take this one and do Z transform of it, green, okay. Z transform of impulse response is the same as the transfer function. That's actually why we have the lowercase h as the impulse response symbol, but then the capital H is the is for the transfer function. Same letter, for reason. Okay. And likewise, if you want to know what is the the transfer function of a no, okay, go away. Huh. There. So, oh, that's not nice to have that one here. Okay, whatever. So Z transform of the impulse response, well, that's what comes out as a transfer function. No magic on it. Okay, then of course when we have the transfer function, I immediately start talking about the zeros and poles. You can actually also see if the system is the FIR or IIR, depending on how many or where the poles are. On this one, we have non-zero poles inside of unit circle, but they are non-zero. So this system actually is infinite impulse response. While this system here, I think last time on the classroom we already found out, okay, 4-point running average filter has the zeros here and poles here for this representation, but for the feedback representation we had also one pole here and also canceling zero at the same spot, meaning that okay, it's still FIR because these are cancelled out and we have this all the poles are, otherwise they are on the origin. Okay. How about step response? Well, same thing, same principle as in the impulse response. The step response is simply just take the step input and take a look what is output. That's usually marked as SN, step response. It has less meaning than in analog systems because we can test the systems using impulse. On analog systems, it's not a good idea to zap the electronics. Yeah. One, unit energy pulse of indefinitely short, meaning gazillion volts. And 1 unit, of course, would be SI unit. 1 joule of energy zapping your electronics. Okay. Anyhow, so for 4-point running average filter, it's just the step response looks like that. Why I have the step response here? Well, that's because that's the way you can then you can start comparing the analog systems with the corresponding digital systems. At some point, in any case, at least in real world, I'm not going to the Moomin world, only the real world. On the real world, when we are checking the real the response of an system, electronic system, we usually run it with a step of some sort of. So this gives just a nice way of doing those tests first by simulating instead of just, running the real test. Okay, couple of pictures. Yeah, and for the running average, what does it actually show? Well, our the step function has very rapid rise, but of course, when you average that step, it is actually a slope, sloping the signal up, smoothing the edge. Wow. Arbitrary signal response, meaning what is the signal, what is the output for certain any signal X. That's where you have the difference equation. On the other hand, difference equation is not actually the most efficient way to calculate the output. For example, this running average filter, you can calculate it at least these 3 different ways. And it's still the same difference equation. Okay. This is the least efficient way. It has 3 additions, 4 multiplications. Each of these steps actually means 1 memory location. The second one has the same amount of memory locations, but only 1 multiplier here, same amount of additions. This here has 1 multiplication and 2 additions. More memory though, but since this one requires 4 memory locations here, this is 1, so total 5. But on the other hand, memory is cheap, but the multiplications will take time, as well as addition is usually, well, addition is usually single cycle operation. But anyways, the rightmost is the most efficient way to calculate it. The same way on this linear time invariant system, there are different methods to optimize the calculations. For example, if we have symmetric impulse response for FIR, then we can actually calculate the multiplication before adding. So it halves the amount of multiplications. Okay. Anyhow, on the arbitrary signal response in MATLAB would be, you have the X of n, but on output you would have filter, B, A, and signal. That's simple. It's optimized for general use. But we'll take a look at that one later. Okay, so that's all in time space. Time space responses. The impulse response, step response, arbitrary, meaning any response. But then basically what we usually, at least on analog electronics, you were really interested about the what is the amplitude and phase response of the system. Same thing here. So what this system responses are actually on frequency space. So we are talking about frequency response. Some mathematics there. Well, although this is more or less non-brainer if I write it a different way here. So we have the transfer function, and if we evaluate the transfer function, well, at e to j omega, where this omega is actually an angle corresponding to the real frequency on unit circle. This is our frequency response. So e to j omega is simply a point in unit circle of z-plane circle, and that omega angle is simply 2 times pi times the real frequency divided by sampling rate. So it's linearly dependent on the sampling rate. Okay, so yeah, and yes, it's a complex number, of course. Same way as in analog systems, you have the complex angle to show the phase difference. Same here. So you can divide this one into amplitude response, which is the this part, and I think, well, that's one way of marking the angle there. Then you have this phase shift. So amplitude response and then the phase shift. Or phase response. Or that could be also e to j theta of omega. Okay. No magic there either. So let's go forward. So magnitude response, phase response. Totally analog to the analog world. And yeah, that's the picture of the complex plane again. And just remembering, okay, that complex angle actually represents the frequency the same way as this j-axis on analog S-plane represents the frequency. Okay, wow. Frequency response of 4-point running average filter, my favorite here. That's one of the things that you can also, of course, calculate. If you have a z-transform of a impulse response that was earlier, it was the 1 over 4 plus 1 over 4 z minus 1 and so on. You just replace the z with the e to j omega, you get this kind of formula, and then you can also use the Euler's formula to cut it into sine and cosine and imaginary number. Was it cosine of theta plus I times sine of theta, something like that. Yes, and you can actually calculate the real the values, which shows that okay, the absolute value there. Absolute value shows that okay, that's not much of attenuation. 4-point running average filter, you get about the stop band attenuation is only about 10 dB. Not a really good filter, is it? Actually, with the running average filter, the best you can get for the stop band is minus 20 dB. So not much of filter, but it actually it reduces the noise, yes. Yeah, and then we have this phase response. Okay, that's interesting. Actually, the phase response is quite linear. Well, on that one, that point, it's a special point. So basically, it's undefined on that point, and then it jumps again on there. But anyways, it's continuously linear. There is a special meaning for the linear phase response. But first, about that frequency, yes, this omega is normalized frequency. And basically, if we know the sampling rate, then it's simply just, if you remember that 2 pi, angle 2 pi means full circle. Basically, which means that we are back to the same location here. Another one, sampling rate over 2. Nyquist frequency. It's here. That's the sampling rate over 2, corresponding omega for that. And by the way, basically the upper half is always the mirror image of the lower half, or the other way around. Always. Meaning these zeros and poles are always complex conjugate pairs. Okay, so for known sampling rate, yeah, that's how you change this normalized frequency into real frequencies. Be careful with this MATLAB or Octave. They do not necessarily have to pi on this formula or 2 pi on the formula. They might actually give you normalized frequencies 0 to 1, where 1 means Nyquist frequency. So its pi is missing. Okay, so again, 4-point running average filter frequency response at sampling rate of 44.1 kilohertz. Okay, there you go. The sampling rate now, the Nyquist rate is there at 22.050 hertz, and we have the notch there. Good. That's the highest frequency. And well, the same way as you wouldn't draw for analog systems the negative frequencies, since they are for the amplitude response of any filter. Same thing here. Negative side, it's just a mirror image of the positive frequency side on the amplitude response. Okay. Wow. This is great. Amplitude response, which was the absolute value of this one. When you start calculating and thinking, okay, we have the zeros and poles of the system. Let me take this one out. So our transfer function was basically either the sum of bk times z2 minus k divided by sum of ak times z2 minus k, or with a product. As a product, you can also write this one as a product from, okay, so z minus the 0 point and z minus the pole point. When you do the magic and also mark the z equals to e to j omega, what you get is the absolute value of b0 divided by a0, and then the product of e to j omega minus zk divided by the product of this one, e to j omega minus pk. All right. My old habits, I sometimes use single and sometimes use parallel of this. Don't worry about it. They mean exactly the same. This just means it's the second norm. That it's on my spinal cord. I cannot help it. Okay. We have a point e to j omega right here. And we have this one, which is e to j omega minus pk, for example, p1 here, or p2, and absolute value of it. This actually means the distance. So e to j omega minus p1 is right here. It's the distance. You can measure it by measuring tape. When you're using same units, then basically this will become unitless. And yes, you can actually do this. I have actually, some years ago, we had a lot of fun. We had a parallel, calculator. Each one of you had different angle, and we calculated the, the amplitude response using this. But okay, we have MATLAB also, so it's a little bit easier that way. But the meaning is quite straightforward. It's the product of distances. Product on the numerator is the product of distance to the 0 points, and on denominator the product of distances to poles. Okay, there, and I have a animation. Let's see, does it work? Yes, it does. Wow. GIF creator. Yeah. So the angle is changing on. So that red line here shows actually the e to j omega, and that's the vector 0 to e to j omega. And then there's the it calculates the distances to the zeros and distance to poles. The distance to poles in this case, they're exactly the same, so it doesn't change. It's 1 all the time. So basically, the amplitude response of the this FIR system, 4-point running average, depends only on, well, those distances. And a couple of special points here. We are exactly at the same point where we have 0, meaning that the amplitude response goes exactly to 0. Same thing on angle pi there. Okay. This is so much fun to watch, but anyway, let's go to the next one. Oh, yeah, I have some, well, yes, strange things. So amplitude response have local minimas on the angles of 0. So wherever we have 0, and then basically on that angle in here, in this case, we would have amplitude response going 0 on that omega 0 frequency. So if that is the sampling rate over 2, then we have in here somewhere we have the corresponding omega 0. We know from this plot that the amplitude response goes to 0. So adding a 0 to the unit circle gives us 0 response on that frequency. So we can already start designing digital filters. Poles we can use to add some gain. So how to use it is, well, if the denominator gets smaller, then this one gets higher, right? So we can actually have these angles. There, another angle, omega x. On that angle, I know that I have local maxima. Which means that I can kind of guesstimate the rest So basically, it doesn't have any other special points. This amplitude response looks more or less like that. Maybe less, but on the second exercise, you all supposed to have quite similar IIR system on the question 3 or something like that, 2 or 3. Okay, so it was a low pass filter. I have a couple of animations here again. Let's see. How will they do? No, work. Let's see. Yeah, this is what happens when you move those zeros on the unit circle. You basically just move the notch angle. So where the highest. Great. I'm now moving the pole from the zero closed. As you can see, the Q factor actually goes close. It's the same thing as in analog systems. When you get your pole close to the this imaginary axis, you actually have the high Q factor filter. And okay, the same thing over. Where did it actually stop that one? Yeah, going higher, higher, higher. So we also have narrower filter here. And there if we start moving those poles, which are near to the unit circle, again on that the angle, then we can move the central frequency of the filter. Okay. Another animation. Wow. Okay. So that's basically how you make a flat amplitude response on the passband, flat-ish. So you just select those on, say, appropriate places, which are very similar to the Butterworth design. Except, okay, this frequency space is differently mapped as in analog systems. On analog systems, the Butterworth filter poles are where? You should remember that better than I do. Okay. Okay, S-plane analog system. Here we have the omega z or j times omega z minus j times omega z. Does this one ring a bell? So second order Butterworth low pass filter has poles there. Right. Third order, you just have those here, here, and here. Quite similar. They are not anymore actually on the circle, but they are in a kind of elliptic formation there. Good. Phase response. Phase response defines the sinusoidal signal delay on the system. So it's actually a time delay at the end of the game. So if I have any system defined by its transfer function, for example, this kind of system, then what comes out would be the, amplitude. This is missing the amplitude response actually. Amplitude response times sine of the same angle plus the phase shift. 3 different cases. On analog systems, you have only one case. It's always nonlinear phase response. You can get near approximation the minimum nonlinearity on the phase response would be on Bessel filter. Okay, but in digital filters, we really have three different cases. Linear phase response, meaning that the phase response can be described as a constant times the phase angle. Okay, that is a very special case because yes, no, that will be constant phase shift, which is different. Okay. The linear phase response actually means, let's take a quick look at what it means. I think it's on the next page, but on the other, I like thinking at the same time. So if we have a linear phase shift system, so we have the sinusoid of omega t going into a system. I'll mark it now. It's a analog system. It helps me thinking. It has basically now that we have the amplitude response on that angle times the sine of omega t plus, if it's a constant, so linear phase shift, it has k times t, meaning that the second part is simply the amplitude response times sine of omega sorry k times omega, not k times t, of course. Linear phase response, yes, k times omega. Okay, so we have k times omega, so basically we have omega times t plus k. This is a constant. So linear phase shift means constant time shift. Okay, meaning that if you have a really ugly looking signal coming in here, different frequencies on it, only thing what this system does for this signal, time reverse operation. It just filters the amplitude but doesn't really touch the phase. It's just a time delay. Meaning, for example, let me make a better example than that. We have two different frequencies carrying the same amount or same information on multiple frequencies. How to pack data on radio. Use multiple frequencies and code different bits into the different frequencies. What you want to have then is that these packages actually stay as packages. So you only incorporate maybe some the amplitude change, but still keep this package coherent. There's no time shift between different frequency components. Very important property for any communication system, the filter. Nonlinear phase response means that, okay, well, it's IIR system. Usually, all the IIR systems are somehow nonlinear. Analog systems are nonlinear phase shift, meaning that it starts to distort this information. Zero phase response is quite interesting, since if you do post-processing, you can filter the data one way, then reverse the time. On post-processing, you can do it. Just reverse the time. So last data point actually comes first into the filter, and do it both ways through the filter, and it removes the phase shift. So it's zero phase shift. But of course, it's not real-time operation, but it's a dirty trick that scientists use. Sometimes even engineers do it. All right. Group delay. Group delay is the phase derivative of, or not, the frequency derivative of the phase shift. So basically, for linear phase response system, group delay gives the constant, which is same as the time delay. It's the constant time delay. It's directly that one. On zero phase response, it has zero time delay, meaning that, okay, group delay is zero. Non-linear phase response system will skew the signal, okay, but anyways, then you would have a, say, varying group delay. And group delay gives basically the time delay of the signal on different frequencies. I think I have some pictures of it. Okay, yeah. Okay, I have a kind of nice test signal there, just a kind of uniform signal and zeros on both sides. For linear phase response, you have exactly the same edges. So the linear phase response system basically means that if you have rising edge or falling edge, but otherwise the shape is the same, then it does not change the shape. It stays like that. Nonlinear phase response, this is, I think it was second degree system. Quite familiar what you get from any analog system. So there's a little bit of overshoot, but then actually it comes as an undershoot for the falling edge. On linear phase response, you have equal amount of undershoot and overshoot for the both rising and falling edge. Zero phase response, meaning that actually you have the filtering capabilities here exactly the same as on the say nonlinear phases, but well, the time shift is zero, and that's why you cannot do it in real time. You cannot calculate these values before you are actually having any data. So, but post-processing, yeah, why not? Good. Spectrum analysis. So now we had the impulse response, step response, sinusoid, or any other response. We had transfer function. We have zeros and poles, how to relate to the frequency response. How about now one more step and going back to the signal and taking a look at the how to analyze the signals. That's simply done by Fourier transformation. The power spectrum definition is right there. So you take the signal xt and calculate the Fourier transform, and basically that's the second norm. You multiply it with the complex conjugate of the same Fourier transformation. In MATLAB, that's how you do it. Okay, with sample data you use discrete Fourier transform. Well, you call the function. You don't have to use it otherwise. You don't have to make the hammer in order to use it, you know. The practically the fast Fourier transformation is the way to go. However, there is a caveat. The fast Fourier transformation works only if the number of sample is 2 to the power of something constant, a integer. So 2024 is okay, 4096 is okay, 9192 is okay, but 8193 is not okay. Okay. Yeah. Then there are some other artifacts. Spectrum analysis. This is a real Fourier transformation what I did for sample data like that with 1000 data samples. On analog world, you can wait for a while until this actually settles into one single peak. But in digital world, you always have this envelope that comes from the fact that, from the physical fact that these signals actually obey mathematics. When you take the Fourier transform of this data, it's not actually just Fourier transform of the sinusoid, but also the window function multiplied by window function. So if you basically some mathematicians has found that okay, if you have a multiplication of this one, it's the same as you do convolution in frequency space, meaning that actually you get peak from the sinusoid, and this envelope actually comes from the Fourier transform of the window function, which you always have since you have limited number of points. So it's like looking from the window. There will be some exercises for that one, but I will just show some nice pictures. Okay, single spectrum is kind of nice, but on the other hand, if the signal was such that you can define it only by one single spectrum sample, it will be really boring. How about if we have a varying frequency on the signal, for example, as in real life? This is another test sequence. It's a chirp signal, meaning that the frequency is changing linearly by time. So basically here we have zero frequency on the beginning, and then it starts, going higher and higher frequency. For that one, to analyze that one, a single the Fourier transform would give you just flat response, flat spectrum. But if you calculate the spectrogram, it actually shows you how the spectrum is varying by time. So there's time on the horizontal axis, frequency on the vertical axis, and then this color-coded picture of how the frequency is varying, how the power is distributed over time and frequency. Okay, soon we will have a break, but anyhow, let me explain that a little bit, since it helps probably understanding the spectrogram better. So spectrogram, time versus frequency. And then can you imagine what that could be? That's actually the ambulance. Dee-da, dee-da, dee-da. And then, yeah. So it's actually the spectrogram is used as a image representation of a sound. The first people to use it were actually, well, non-military persons to use it were the ornithologists, describing how different birds actually are singing. So they could have, or, and just drawing that kind of images on the on the margin of a bird manual. Okay. Then there was the Second World War, and there were also another applications for the this one. And now there are plenty of other applications. Submarines. How to find out if a submarine is actually ours or the enemy. You listen, signatures, and then drop bombs and say, oops, oh, it was ours. Okay, but let's have a break and then come back at 3:15